Now today's thing we will start lesson 4, in which you have the lesson 4. This is for the problems. That 3 interesting problems we are going to study, which will make you to learn the physics part of it, plus some Mathematica course also you can learn. Okay. This is what the plan now for this session. So we'll start from this problem of example 2.1. Maybe you can read this, then try to think about the problem, how to solve this, and then try to uh, find out what could be the simplest way to write the Mathematica codes, understand them, then what are the easiest ways in which this Mathematica can be used that we can understand about this problem and solve the problem. So read this. Train number 1 and train number 2 are moving side by side on a parallel horizontal straight tracks. At the time t equal to 0, the train number 1 starts from rest and accelerate at a constant rate a1 equal to 0.5 meters per second square. Also at t equal to 0, the train number 2 passes the train number 1 while moving at a 20 meters per second in the same direction as train number 1. Same direction as train number 1 is accelerating but decelerating at a rate of a2 is equal to 0.2 meters per second square. So this is accelerated with the 0.5, moving on. At t equal to 0, the train number 2 passes the train number 1 while moving at 20 meters per second in the same direction. While it's moving, that is the train number 1 which is moving. Okay. No, I think train number 2 which is moving, that train number 1, and at that time the train number 1 is same direction, it's accelerating. But the deceleration at the rate of 0.2, no, at t equal to 0, the train number 2 passes train number 1 while moving at 20 meters per second in the same direction as train number 1, which means train number 2 is moving with a velocity of 20 meters per second. Okay, same direction as train number 1 is accelerating, but deceleration at a rate of a equal to 0 meters per second square. So it is moving with the 20 meters per second, but it is decelerating with the value of 0.2 meters per second square. Find the time at which the train number 1 passes train number 2. Time at which. To determine the distance from start at which they pass. So read it. One more time you read it. Then think about what could be the equation of motion for them. Then what should be done on that to solve this, finding the time at which the train number passes the train number 2 and determine the distance from the start at which they pass. Okay, which means at t equal to 0, it's they're passing each other. Okay, so now the issue is that we have 2 parallel trains that are moving side by side. Okay. Is it okay? At time t equal to 0, train number 1 starts from rest, which means your initial velocity equal to 0, position also 0, and accelerates at a constant rate a n equal to 0.5 meters per second. So it is accelerating. Also at time t equal to 0, at the same time where at t equal to 0, train number 2 passes the train number 1 while moving at 20 meters per second in the same direction as train number 1. Train number 1 is accelerating. Same direction as train number 1 is accelerating, but decelerating at a rate of 0.5 meters per second square. So which means this is the deceleration for the train number 2. Is crossing at time t equal to 0 of the first train with 20 meters per second is the speed. Okay, that is the velocity of that second train. Okay, find the time at which the train number 1 passes the train number 2 and determine the distance from the start at which they pass. So if I look at the first train, this is sort of, because you have acceleration is given here, the initial position and velocities are 0, therefore x1 is, this is what your equation of motion. The first part is clear. I hope it's clear for all of you. The problem should be read properly and then set the equation now. This is the equation which you are trying to set for the train number 1, and make sure that this is proper for the statements whatever has been given here. Is that right now? Let's write down this equation and then come back to this. Is it okay? Right? X2 at time t equal to 0, V0, okay, just passing with a velocity 20 meters per second. When this is starting, this is already moving with a velocity of 20 meters per second with a deceleration of 0.2 meters per second, which means A2 is minus sign. Therefore, it's a minus here. T square. This is X2. So I hope this will be clear for all of you according to the statement of the problem. Fine. So you should say yes or no, then only I can proceed.
Yes, sir.
It's clear for all of them. This must be clear as per the statements whatever is given. They have made this equation. So now there are setting up so that the position x equal to 0 locates the trains at t equal to 0. If I set this x position equal to 0, locates the train at t equal to 0. That is, this is x1 and x2, where this one is there. We need to find t1 at which x1 equal to x2. That's what it means. X0 means x1 equal to x2. Where do they have the same displacement? And what time that's going to happen? Because they're all moving in their dynamics are different. First train dynamics is different from the second train dynamics. But after a long time, because of the difference in acceleration, they may be meeting each other somewhere. That is what this problem states. Because this acceleration is different from this acceleration. This is starting from rest. This is already moving with the V0. So therefore, all these things that are happening. And to solve this problem, what we have to do, we need to find t at which x1 equal to x2. That can be done. So I think it's clear for you up to this point. Otherwise, you cannot think what is to be done further. Okay, one way to think about this problem, I can plot this x1 and x2 as a function of t. I do not know where they're going to meet, but I can plot the curves. Is it not? Is it possible? x1 and x2, I can plot it independently as a function of t. If they meet, they will be meeting somewhere, no? Will it happen?
Yes.
It will happen. Okay, let's see. X1 is this one, which is defined according to this. X2 is this one. They are defined well. And the parameters are given already. Yes, A1 is 0.5, A2 is this, V0 is 20 meters per second. Okay, so suppose if I make a plot, let me take a plot now. Before that, I'll enter these statements. Global, see, I think there is some problem here. There are no symbols matching. Oh, initially, nothing has been defined. Probably you can see that this is x1. Now, if I enter this, that will be removed. Yeah, that is what the problem. Doesn't matter. So this is x1 and my x2. Constants are defined, and I am plotting this. Do they meet now? Are they meeting? They are still separated now by a distance. You can see this is x1 meter, this is x2 meter. They are not meeting each other within 10 seconds. Do they meet?
No, sir.
No, they are not meeting it. So what you can do, one possibility is, I would like to scan it T end. Okay, I can manipulate. Manipulate what? Manipulate what? I am manipulating the end point where they are till the meet I wanted to go. So TE. Now let me start from already 10 we have come. So let me take from starting from 10 till 10. 10 to somewhere about 100 I go. Shall I do that? Because each time when it plots, it goes starting from 10. T0 to 10 is the first plot. Okay. And if I change the TE, what happens? I'm going to extend the time now. I'm extending it, extending it, extending it, extending it, going on, going on. There is a change now. You are able to see that approaching each other. They are approaching each other, approaching each other. Somewhere they are met already. Okay. Is it right?
Yes,
These
sir.
two trains, as a function of time when started moving, somewhere about after 60 or between 50 to 60 seconds, somewhere they are meeting. Is that right? Okay. This is the time axis. This is curve 1. This is curve 1. This is red. This is x1 and blue is the x2. They met somewhere. This is the meeting point. Right? Okay. So if I identify the meeting point, then I know where, at what time they met and what distance. Both are known to us. If I go beyond that, they will be separated again. Okay. So is this clear for you? Now you tell me what mathematically one should do to get this point. So what you have to do is equate x1 to x2. That is what this point. Is it right?
Yes, sir.
Therefore, it's fine. This is the displacement for x1 and x2. They are meeting at this point. When will they meet? That is known to me. So you have to solve these two equations with this condition. And when you solve that, you follow the procedure of solve. Okay. And this A1, A2 already defined. I wanted to clear that because I want to get an equation form. Therefore, I clear those numbers and then set it in the form of an equation. Solution 1 I am defining as solve x1 equal to x2. That is what the equation which we have used it. And double equal I am using it. Okay, because this is an equation that has been set and in which I am going to find out what is the time at which that is going to happen. When t equal to 0, of course they are meeting. When t equal to twice the velocity of the second train divided by a1 plus a2, this is the acceleration. Total acceleration of that. Okay. So now let us enter this. I'm able to get the solution here. This solution I am using the rule to find the t meet. I'm redefining as a t meet is t substitute this solution. The second solution which I am taking it. First solution is 0. I am taking second solution. Therefore, I am using a double bracket 2 that has been taken and t is assigned as a t meet. This is what your t meet. You can go beyond that also, but we have this is this point at which it's going to meet. So I know the t meet, and what is that t meet time scale? If I wanted to have that again, I have to copy this. Get it? Copy, put it over here because I need the parameters to find out what is the t meet. So what I do, just enter here, shift enter, and x1, and this, and I think 1 minute. This t meet should go even 0 above that. Cut and paste over here. T meet from here. Because I have to get this time. Now, if I shift enter, these parameters are available, and the t meet is already has been defined as 2v0 by a1 plus a2. That is being evaluated here. Okay. Now, x1 is the distance, which is defined here. X2 is the these two are the distances. Okay, for the train 1 and train 2, in which what is needed is the t. T is the common point where they are going to meet. Therefore, I am substituting the t meet here for x1. I have done that, which means 816.32 meters at the time of 57.14, they are meeting. The distance of this at this time they are meeting. Similarly, for x2 also you can find out because their meeting point Therefore, both will be same. Is it not? Both would have same displacement should be there for both. This is the meeting point for x1 and x2. X1 must be equal to x2. That's what the problem says. Both parallel trains meet. Train meets at 57.123 seconds at a distance of 816.33 meters. Now, okay, what you do, you go back to this, shift enter. So, these numbers should be graphically verified. Is it verified here? Check it now. Get the coordinates. Where about this? 57.23 something plus 820. How much is 27 or 816? So this is the meeting point. Okay. Is that clear? Is this problem is clear for all of you? I hope it is clear. Yes, some questions. Yeah. Any questions? Shall I proceed next?
Yes, sir.
Okay. The next question is, instead of decelerating, if it is accelerating with the 0.2, when and where will they meet? Can you think about and tell me the answer? Or you do it and tell me the answer. I'll give you minutes. Repeat the problem. Or think and are they going to meet or they don't meet at all? First thing. Second, if they meet, when will they meet? Where will they meet? Instead of a minus, I put a plus, which means I have to add a minus sign here. It will be automatically plus, is it not? I can explore it now by changing the number here. Put A2 equal to minus 0.2 because already there is a minus sign, minus plus. So it is, which means A2 become a positive value. It is going with an acceleration speed. If that is the case, are they going to meet? This is just curiosity to know about it, whether they meet or they don't meet at all. But I have a feeling they should meet because their accelerations are different, is it not? Do you think so?
Yes, sir.
Because this is 0.5, this is 0.2 no, positive value I'm taking now. Okay, how do I convert into positive? By putting as a negative sign here. Okay, I just changed instead of positive, I made it as a negative sign. Just a minute, 1 minute, I'll be back. Okay, start again. Tell me what will happen now. It is instead of negative deceleration, if it is acceleration, I'm sure that they will meet. That much I'm sure. If it is more than 0.5, then they don't meet at all. Okay. If it is less than that, there is every possibility they can meet. Okay, if that is the case, I just change the number here. Then continue. Make a manipulation and look at things. And up to 100, let us check. Do they meet? Do they don't meet? Are they meeting now? They're not meeting. We'll go to something like 300. Shall I make it? End point I'm taking to 300. It seems they are going to meet somewhere. Yes, it's going to happen. They are meeting it. Where? Between somewhere about 130 seconds or so, they are going to meet. You can find out. See, you see how much distance they discovered. Already something like 4,500 meters have been covered by them. They are going to meet each other. Okay? Is that right?
Yes, sir.
Fine. Now what I do, I wanted to check what will happen if it is 0.6, which is greater than that. I just wanted to have some idea about. No, they are not meeting. I'll take about 500 now. 600, are they going to meet somewhere? No, they are not meeting. Even after distance of say about 1,20,000 meters. I'll go to something like 1,000 seconds. See? They're not going to meet at all. Is it clear for you now?
Yes, sir.
So when you can see that the other one, which is though they are parallel, but this acceleration is 0.6, which is greater than 0.5, and they don't meet at all. In spite of traveling something like 3 lakhs kilometers, they're separated. This is what the thing that happens. You can see that these numbers, how do they play in describing the dynamics of the train. And when you are describing the dynamics of the train now, we assume now train is a point object which is moving. See that? Such a big object, we treat them as a point object, and we try to describe the dynamics. See, that's how things has been done, and it is possible also for us to predict something about the motions of such a huge object, treating them like a point object, and then try to describe the dynamics. Okay, so now I just go back to this. So which means point 2 also they are going to meet, which we have seen now. In spite of changing the acceleration, point 2. What happened to this? So I should enter here and then check. They meet. They are meeting here somewhere. If it is a point 3, do they meet somewhere? It will be surely they meet somewhere, which is much beyond that. This point 4. Enter here. They're going to meet now. Yeah, they're almost close to each other. They are parallel now. When they come back to, what will happen now? This is the important point which I wanted to bring it to your attention now. What happened now? This should be now. And what happened? -0.5. The initial speed only. They already almost become parallel with a small distance. No, this is huge distance in spite of that. Suppose it gives an opportunity for us to explore meeting at 40 meters when it is, what is the deceleration is 0.5 because of the initial velocity which it has. So that is what the thing that happens. Okay. There's some initial velocity, no? With that, they're going to meet at this point. So this is what the situation that you have when you have two parallel trains that are moving with a different acceleration. Now the acceleration which is according to the problem is equal to 0.2. Do it now and check that numbers what they have is This is question of, because our scale is too high now. That is why this is happening now. So reduce the scale now, you can clearly see this variables. So this is what the result that has been done. And you can, by doing the process, we just check several other things. And mathematical learning is now, here we have the code is, that solution has been defined with solution 1 and substituted back by using this, because it's a rule form taking the solution result 2, substituted this. This is available for me to use, that has been used for finding the, with this parameter, what is the meeting point of the time, and then at what distance, because x1 and x2 is available, we just calculated and we found they are meeting, they are equal distances now. This is one of the interesting things that happens in this problem. Now, we are solving the equations and substituting back also, you can cross check it. So one such thing, which you are familiar. Let's take this equation. You know, this is a very famous equation, no? A famous equation or not? The quadratic equation. Okay, what is the solution to this equation? Which everybody is familiar. Minus b square root of minus plus minus square root of b square minus 4a divided by 2a. This is the minus here and this is the plus here. That is what the two roots of this quadratic equation which has been solved, we have found it. Now solution has been obtained and the equation is already available. I am just substituting the roots what has been found by using a rule. Equation is this. You can see how it is being equation equal to single equal to with an assigned double equal. This is an equation. Okay. This is also possible to define like this with a single equation. Both equal, single equal and double equal can also be used. And this is designated as the equation 1 that is being taken here to solve for x. So please note that is important for us to use at later stages wherever you have such complicated equation. Sometimes you have a n equation, n unknowns. But I saw something like 250 equations, 200 unknowns. 500 equations, 500 unknowns also can be solved. It can handle it. Okay, it's not a big deal at all with this. Okay, equation is now quadratic. Solution has been found, and we are having a 2 roots now, and we are substituting the roots into the equation. If this is root, then it should satisfy to this equation and should become 0, which means equation should say that true. Both of them are equation solution to this equation. But after substituting simplification, after substitution to the equation 1, both of them, you see the equation appears to be like this. That is the big equation. But actually this should be simplified. Okay, substitute the solution and simplify. So I'm going to check that. What is the problem here? What is the mistake which I have done? Can anybody make out? Neither list replacement rules nor valid dispatch table are so cannot be used for replacing and so cannot be used for replacing. What is the mistake? Any guess?
So the solution you put with a capital letter.
That's right. So this is already it's indicating as a blue. If it defined variable, it's there. The blue will be disappearing. So I just purposely entered the capital S2 just so that that's not be satisfying if you make a small mistake there. So if I change this to yes, automatically the blue become black. You see that? Which is already available. That's what it means. Okay, now if I substitute, it is true. Both the equations are satisfying this quadratic equation. Okay? Are they satisfying now? It is. You can see x1, this is root 1 and root 2. Substituted back. How do I do that one? Because I have equation which is already defined in this form. In this, I'm substituting the solution by using a rule /dot, which means this will be taken and substituted for the x into this equation and simplified. When I do the simplify, It says true, true, which means they are satisfying this equation. That's what it means. Okay? So fine. Right. I hope this is clear to you, and the way in which we are handling these solutions and the equation, that should be clear for you. If you have any problem later on, you can refer it here and then try to check whenever you have the equations, solutions are available. How to substitute and check it, and you can reconfirm it, whether they are satisfying or not. Next is wonders in quadratic equation. We're going to see something great. So you have a typical x square plus x plus 1 equal to 0. I want to find the solution to this. This is going to minus 1 by 3, 1 by minus 1 whole power 1 by 3. Then this is minus 1 whole power 2 by 3. You know what it is? It's given here. It's a complex quantity now. Complex expand. If I do this one, minus of 1 by 3, minus of 1 whole power 1 by 3 is minus half minus of I square root of 3 by 2. You can check it. You know A how much, B how much, C how much. Follow this equation and make sure that you will get exactly the same results as what has been given here. But this has been given in this form, minus of minus 1 whole power 1 by 3. This is plus minus 1 whole power 2 by 3. Both are complex quantities having a real part and imaginary part that can be checked. Here you can see this is the minus, this is the plus sign. I just use the complex expand. It means complex numbers can be handled using certain statements that are available. This is one new thing that you are learning now. This is complex expand. So any complex function that is available, it can be expanded to a real part and imaginary part, ABS value, argument can be found, or tan can be found. All this is all possible by using this complex expand, in which those statements that can be found. For example, I have this. Okay, I wanted to remove this x equal x arrow x arrow. What do I supposed to do? Can you suggest? Then I want to find out real part separately, imaginary part separately. So what do I supposed to do? I'll give some name for this. So yes, complex solution. Yes. So CSOL1, complex solution 1. Will I do that? This is what the result that I have. Then what do I supposed to do? X, and then substitute by using this rule which is there as a two roots as complex SOLN. If I do this statement now in Mathematica code, if I write like this and shift enter, will remove this because our x is being substituted, which is already available with this COL solution. C solution 1 is this, that is substituted back, and you would get this one. Okay, fine. Now what I can do, I want to separate the real part, imaginary part, find out ABSC value. Okay, all that need to be found by using a complex numbers or a complex expand. So I have a statement COMPLE complex expand, in which I wanted to have now the list be created for a real part of first one, then imaginary part of the equation what you have here. Then you wanted to have a ABSC value, ABS absolute value can also be found. So what you can do, I will define this as a CR, complex roots, that has been defined there. See, I'm just using the C solution here. X is there. I made it as a complex root. Now this complex root has a list that contains two roots that are available. I want to expand that with this variable CR, the imaginary part of the CR, and this is absolute value of the CR. Let's see what's happening now. What happened? It's an indication of an error here. That error is bracket I am used to start bracket. Okay, this is the real part. This is the imaginary part of So the real part, there are two of them. Minus of, correct? So this contains two such things, two complex numbers. Real part of both has been taken. Imaginary part of both has been taken. What is the absolute value of that? It will be 1 and 1 for both. Okay. So this is how the complex quantity that can also be handled by using this complex expand. And this is complex expand which I used here to expand this minus of minus 1 whole power 1 by 3 in this form. It has been done. Okay, clear? So x cube or x square plus x plus 1 is like a polynomial of order 2. 1 plus x square. An equation has a complex root. And these are the roots of this equation. Next, suppose two of them are minus. Okay, what would you get? This is going to be, we are finding a number which is root lying close to 2. So we are using a find root. This is a real root. We are finding it by shift enter. So the difference between this and this is there's a minus sign here, there's a minus sign here. X square, which means x square equal to x plus 1. Here x square equal to minus of x plus 1. That's what the meaning of that. Okay, we will enter it and this is what the number. And I have written something. Root is a golden ratio. This is golden ratio number, this fantastic number. I do not know how many of them are familiar with this golden ratio. Okay, and you see Mathematica has a golden ratio, which is already defined there. Golden ratio, I asked for the number, it has given that value. Okay, get it now? Any idea what is the golden ratio? Okay, we'll see that. Okay, now we are finding the solving it and finding the two roots. We have found one of them, and we want to have a solution to both the roots now because it's an x square. There's two roots that are available, and see now it is substituted within one statement. There's a difference between this and this. Here we have written the equation, found it, and here it is defined the equation for the solution, and then substituting back. But it is can also be done directly. Solve it and substitute that x. I'll get these numbers. So this is the way we will improve and understand more efficient way of writing this Mathematica course. You find the difference now? What I'm trying to say? You're able to get it now? See, I'm going to use same thing. I'm going to rewrite it. See, x, put a slash dot. Whatever you have written for 2-3 lines, I'm going to write it in one single line. Complex expand. Whatever which I explained in a 3 different lines, I'm able to get it here one line. Okay? Right? Suppose if I do the complex expand here itself. You can see the difference now. Solving, substituting, and then looking for the complex expand. Is it that? Here also it can be given, or at the end it can be done. Okay. Or if you wanted to have a real part of here, you can just give a real part. See, I'm going to combine many things together now. Find out the root of that, find out the real part. It has been taken. Find out the imaginary part. It has been taken. I want to have both real part and imaginary part here itself. You see how efficiently one can improve your. Okay. This is the real part, imaginary part. And I'm going to say this is the real part of that, imaginary part of that. Okay. Make sure the things are defined properly. Brackets should be proper. So whenever you use bracket, as far as possible, try to open and close it, you enter in between, so that you will not have a confusion. So now what is that it does now? Find the solution, substitute it, then it takes the, using the complex expand, Real part has been calculated, imaginary part has been calculated. All goes into a single line. So, without even substituting or defining the left hand side of this, started with this x, okay, slash dot. This is in the form of a rule that's being substituted here, and x has been found. And therefore, in that, I have a number like this. That is, we have found a number which is minus of minus 1 by 3 and minus 1 whole power 2 by 3. That is what we found. That has been simplified. The whole thing has been done in a compact form. We are able to get this result. Okay. So, after learning codes properly, then you would start thinking about like this. Because we don't have to write so many lines. We know what we are trying to do. It is known to us. It can be done comfortably. You can do the same thing here, whatever we try to explain here. Okay? Whatever I have done here, you can do the same thing here, whatever it has been done here. For the quadratic equation, instead of writing equation 1 and then making the solution and then substituting back, no, not at all necessary. Just do like this. You can check it and you will find the result. I hope it's clear for you now. Is it not? Nicely we have combined it. This looks very complex, but it is really, if you decode them one by one, like this, it's going to be simple. So that's how things have become made comfortable and use it for our computation. So let's come to the x square minus x minus 1. I said this is the find the root. One root has been found. And this happens to be a golden ratio. And maybe I should explain what is a golden ratio. You're able to see the graph now? Is there any golden ratio sheets here? Okay, I'll explain. If the whole thing, if you take 1 unit, and this must be 1.6 times of this y-axis. This is what your golden ratio. You follow? Y-axis is, or x-axis is 1.68 times that of the y-axis. X-axis is, you can see this, width is bigger than this by what amount? By a golden ratio. That is what your golden ratio, which is here. So this x1, x2, look at the scale. Okay, if I compare this, if I take a ratio between this length to this length, it's going to be 1.68, that number. That is what your golden ratio. And if you want to check that, you can check here, plot, all plot by default has been given as golden, aspect ratio is golden ratio. Okay, change the ratio, for example, you have an aspect ratio for the plot. You know what is the, you're able to see? What is the error? Remote. Okay. Now, see, I'm going to change the ratio now. See, what is the effect? If I make it 1, 1. See? This is 1 unit, this is 1 unit. If I make 0.5, you can see, this is much longer, which means half of this. This is twice. Okay. If I use golden ratio, that is what by default is there. Let's see, this is what the golden ratio is 1. I think it should go other way around. This is higher than this. I think it should be changed. Which means, how do I do that? Today, this is what the actual graph. Okay. You get it now? 1 by golden ratio. They do that. This now will be automatically y-axis and x-axis will be getting a relation connecting in the units of a number. This is 1 unit of this is equal to 1.68 times this unit. That is what the golden ratio. Okay. Is that clear? I hope it is clear for all of you. And this x and y can be all the time. You can manipulate with the ratios and then get the graph in appealing form. For example, if when you make a real part and imaginary part of a plot, then the aspect ratio must be 1 so that you will then extract the information precisely. Okay. So now here, one more thing I want to see. See, this is the control which you have. The control placement, instead of occupying the whole thing here in the left side, I can change this here by control placement. I'll make it top. Okay. You see what's happened to this figure. It's getting shifted again. Now the control placement is at the top of the picture what you have here. This will be easy to visualize. So this is already, you can have it at the bottom, okay, left, right, all possible options that are there. You can explore them. But this will be more convenient to look at it. So these are some of the things that you should learn. So now you can see scale variation will appear as if there's something strange happening. Nothing has happened. Your numbers are almost identical, no change, except the graph appears to be different. That's all. So these things you should take care of it. The golden ratio is something very, very interesting. And what will happen? The golden ratio is the equation of a quadratic equation of x square minus x minus 1. Okay. Now, you can see the difference now. X square minus x minus 1.0, if I make it, I'll get the root in terms of decimal numbers. Okay, 1.7 with the integer and a decimal. If I remove that, there is nowhere any decimals are involved. Then I'll get half 1 minus of square root of 5, half 1 plus of square root of 5. This is also a golden ratio. Okay. The sense that is 1 is minus 0.6180 before, and this is 1.61. This fraction is appearing here with the minus sign. Beauty of that is this fraction is appearing here. Is that right? This fraction is appearing here. Okay. Now this is solved with an integer form. And this integer can be converted decimal by using a numerical value. Right? I'm taking the integer part of this minus this. Hello? And 1 plus square root of 5, that is second part divided by 2, there is a square root of 1 by 5. This is an additional term which I am adding, which is common for both. Okay? That's not there in the root. Our root has been taken out? No. That's fine. Only root is this additional term, 1 by 2. If this is done, there's something fantastic happens. Let's see what is that going to be happening. So I'm just taking an integer form. Then I'm raising the positive or the one of the root with the positive sign as an n, an exponent n. And this is also with the same exponent n. Where is the n? And get the number numerically and take the integer part of it. That is being defined as fn underscore. So this is the function which I have defined like this. We will see the purpose of that. Is it clear for all of you? This is the root. Okay. So you can see the beauty of the natural numbers. This is the root of this equation. That root, I have taken the positive root power of n minus the other root of this. 1 minus of that's also with the same exponent. Only thing I divided by each time by 1 by 5. That is 1 by square root of 5 that is there. Then take the numerical value, which gives the fraction. Then take out the integer part alone. Okay. If I do that, what is that going to happen? That is what our interest. I'm going to check now. Okay. Where do we have to start from here now? X, solve. This is what the number, and fn also has been defined. Okay, I'm tabulating n for a different n, 1 to 15 table. This is being called every time, and I'm getting for every value of n, 1, 2, 3, up to 15, these numbers I'm getting it. Okay, I've already defined this is a Fibonacci series. You know what is a Fibonacci series? Okay, that's interesting. Add previous two numbers. You get the next number. 1 plus 1, 2. Okay, get it now? 2 plus 1, 3. 3 plus 2, 5. 5 plus 3, 8. 8 plus 3, 15. Sorry, 8 plus 3, 8 plus 5, 13. 13 plus 8, 21. Going on. Okay, can go on. Go on like this. And this is an interesting series. Great numbers. An amazing numbers. You can have the numbers are like this. And this is the 100th Fibonacci number that has been found. And what does it mean? If I add this number and this number, I'll get this one. Okay. Any number if you take, add the previous two numbers, I have the current number. That is what is happening with this number. I do not know how this is happening. This is the beauty of the simple quadratic equation. Okay. And has such an amazing features. They're all really amazing to look into. I was thrilled when I looked at this equation and the solution with the quadratic form giving such an interesting information. Okay, you can start from here onwards. You can go on any numbers. Okay, it all depends on the capacity of your computer. Yes, Mathematica can handle the numbers of as big as possible. Okay, right. So this is the 100th number. You can see that 35422, 35422, which I have found separately. F100. Suppose if I ask for F, say let me take 500. That's big is that. You can count how many number of digits that you have in this. And I go for 1,000. That's the number of digits. Okay. See the greatness. You can count the number of digits that you have here also. That's also integer digits that can be done. So this is really beauty. The quadratic equation of x square minus x minus 1 equal to 0 has so much of interesting information that we are able to get it, and we can really appreciate the importance of the numbers, and you see how intense these numbers are. See, it goes up to this. How do I count the numbers? You can count it. Okay. You can count it, it's not a big deal. So we'll remove this one, because unless it is occupying the space, we'll come back to say about 40 digits up to 40 numbers we generate. You can cross check it, okay? It's fine. Now we can write a small program to confirm this. Add two numbers, we'll get the current number, and add the again previous two numbers and get the current number. This is what the number. So previous two number is 1 plus 1, 2, 2 plus 1, 3. You write a program like this. F of 0 equal to 0, F of 1 equal to 1, and Fn of underscore assigned like this is equal to Fn equal to Fn minus 1 plus Fn minus 2. This is enough. That's all. You can compare it now. Tabulate Fn with the Fibonacci already defined in Mathematica, which is already defined in the Mathematica code. This is what the Fibonacci number. 1 to 20 numbers of this program and Fibonacci, which is defined in Mathematica code. They are one and the same. These two lines are enough to generate such numbers. Okay, this is what your program code for getting the Fibonacci number. So start from, just check it now for n values, and it will automatically see that the first one is 1, second one is also 1, 1, 1, which means 1 comma 1 means this is from the Mathematica code which is already built in. This is the program code which we have written by using these two lines. That will be there as Fn. Now you can see that is being generated. And you can go up to 40 to confirm it with the quadratic equation which we have generated. What happened? Is there anything wrong now? You found a mistake? Is there any mistake? No mistake. Okay? Can you correct it now? Yes? Help me for correcting this. I'm not getting the numbers. No? You don't want to help me? Yes? Any suggestions, please? I want to get Fn properly. I'm just getting F1, 2, 3 up to F40. Okay? No? You all feel sleepy probably. Fine? No? Answers for this.
Sir, we have to define n here also.
N is defined, no? N is going on, or both is common. See, this has not been given as an input at all. It is just see the number here, input.
Yes.
So unless you give that, no, it's not possible for you to get it. So that is what the missing point here. And you see, now you will be getting it. You should be careful, whatever you should try to look at it, and you should be in a position to locate when there is an error. Phone. Okay. Is it fine now? I'm going to show you a small video, maybe sound you cannot hear it, but this you can check it now. How interesting is this number of this 1.68? Okay. Video may not, audio may not be seen, but anyway, you just try here and just check. We'll skip the ad, and there are other things that are coming on it. Skip the ad. So I wanted to show you through these are Fibonacci is connected, and maybe this Fibonacci can be seen here. Yeah, you can see. He's trying to say that there is going to be Fibonacci. This 1.6 times, this is 1 time. You have it in your hand. Okay. Next, he's going to show something. You can see from elbow to here, 1.6 is 1. Okay. Next, in the hand, from wrist to here, there is 1.6 and 1. Okay. Look at here, the fingers. So we have a golden ratio with us. Okay. The human body has a lot of places there you have. This is what she's trying to say, that there is a 1.6 times things are available in our body itself. Teeth you have. Then your ears, nose, face. He's so excited to explain that. You see, in ears, you have this business of 1 and 1.6 times. See, here, even the brain. Okay, this is the RNA or DNA. Then pulse, heart pulses. Okay, you're surprised to see. He's showing that the greatness of that numbers. Not just constant, 1.6, it's something. physical constants and the so-called the Kelvin business. These are in the evening. So I will close it. When you find time, just enjoy this one. For 10 minutes, he's trying to justify how great is this natural number, so-called golden ratio. So mind blown. I close this now. See, there the music instruments. So, and even the piano has, and then you have the big building structures. No? You have this. See? So these are something great. I think audio is not working when I'm using this mic. So, you know, where the ratio sits here. If I take a ratio between these two numbers, they follow almost every time 1.6. That's what the meaning of that. What I'm trying to say is that you take a, I just wanted to confirm that. How do I confirm that golden ratio existence in this? Ready? Copy. Paste it over here. And I wanted to take the ratio between Fibonacci of n divided by Fibonacci here, ratio, if I take n plus 1 divided by n, what would you get? This numbers. And that you convert in a numerical form. See the beauty of these numbers, you see? Initially it starts and then getting converges to 1.61803. Started. You go any number, any length of number, you would see the same number. Okay. Ratio between the n plus 1 divided by n of the Fibonacci is constant. That is the golden ratio. Okay. So I feel that it is something really exciting to see the natural numbers. These are about this simple solutions in quadratic equation form. And of course, we have a t square and t. This is also quadratic equations. They also have a lot of information. So we understand the quadratic form, and that has an application of unlimited application that we are able to find now. Okay. Yes. Now you can practice now. One thing is, I think all you have an access now to the laptop with the Mathematica. Again, all of them must be having now. Do you have it now? All of you have access with this Mathematica program, with the Mathematica software and sitting with the laptop?
Yes,
okay?
sir.
Yeah, that's right. Now, you have a digits. 4 digits are there. Number 2, 2, 2, which is in the list. You play with this now. Find out what is the biggest number that can be generated with this 4 digits of 2. Play with that and tell me. I'll show you the possibilities. It's something like that, like this. This is the number, and you can see this is the number that I have. Correct? Only 4 digits only. Don't try to do that 2 divided by 2 minus, or 2 minus 2 divided by 2 minus 2, which is going to be 0 by 0. and 2 divided by other form where you have a zeros. So don't take a negative sign of these ones. You use only the exponent raising it, and other ways whatever you want, and then make sure that you are able to predict the biggest possible number. Okay, you can do this also. This is also another way to do it. This is the number. Okay, spend your time for a minute and then tell me what is the biggest number that's possible. Can I do this one? That's also another way to do it. Any other possibility? What are the possible things which you have explored now? One is over. This is 2. This is third one. So maybe this is the number of digits are 5, and here you have another 5 digits, but this is bigger number. So I'll put this into this place now below this. This is the next big number that's possible, and this is also a big number when compared to the previous 2. Okay, this is another way to do it. Next, other possibilities. Can I do this? Possible? Yes, bigger. Any other possibility? So you have number 1, this one. Second possibility is this. As you said, this can be removed because it's already repeated, and that's a small number. This is the first small number. This is another number which you have, and then 2 power 222 that also been explored. This is the number. Then next. Any other possibility? I can have 2 power 22 power 2. Possible? Then shift enter. This seems to be bigger. So we have 1, 2, 3, 4, 5. Okay, what about other possibility? Two power 2 power 2 power 22. What is the number? Is there any other possibilities you have? You can try this. This is the simplest possible result that you have. Multiply here. And other possibility is 2 into 2 into 2 to 2. Okay. So you have 16. This is 484. This is how much is this? 2 digits. 3. So 5 and 5, and this becomes little bigger than that, and this is still bigger than that, and this is also seems to be bigger. And what will happen here? Any guess? See, so hard. So your screen is filled with only numbers. So now this is the biggest number, and you can count how many number of digits that you have. And I will leave it in exercise and think about it. Is it possible to read them and count numbers and cross check it? That number of digits can be counted for each cases and conclude that this is possible biggest number. Okay, now I'll give some hints for this to how do we approach this problem. Because given problem is 4 digits are given, and I'll take first 3 digits of that and look for the combination which combination can give a biggest number out of these 3 digits. For example, I have it is something like taking a 3 digits together now, 2, 2, 2. We'll explore. What are the possibilities that are here? So 22 power 2, 482 digits. Then I can have other possibilities, and one of the possibilities where 2 power 22 seems to be the biggest number that can be generated out of this. And this fellow, this number, it goes and sits to the power of this 2 power of 41,94,304. That has been taken as an exponent here, 2 power of 41,94,304. Okay, which means this 41,94,304 times you have to multiply 2 into 2 into 2 into 2. That is what this number. That's why this is huge number. Okay, so this huge number, you have to count the number of digits that you have, and you have to tell how much digits that you have. So there are Mathematica statements that are available that you can explore them, think about it, search for the statements, which I used to tell to the student that this is the interesting problem, because if you start count each one of them for 1 second, and if you try to do it, it will take 70 years of your lifetime to complete this. It's something like 12,62,311 numbers already here. In addition to that, this should be added. Okay, now your integer, you may convert it to integer and count the integers, and then tell me the number. Think about it, and it's possible for you to do it. So now you can see this is the powerful tool to explore these such huge numbers. We do have in physics smallest numbers and biggest numbers. Do you have any idea what is the smallest number that we have been using it? Can you just suggest one smallest number that you use in physical problems? Smallest number. No idea. What about Planck's constant? This is equal to 0 point followed by how many zeros you should have? 33 zeros and then 624. That is what the number. Similarly, you have on the higher side, you have bigger numbers. All these numbers can be handled without any difficulty when the computation capabilities are this much if you have, then there will not be any issue at all. Whereas this is not the case with other softwares like Fortran and other things where you have to declare how many number of digits that can be handled, and if you go beyond certain level, it is underflow and overflow. Okay, here it is not so. You can handle with the numbers of such a high intense number that can be handled. So this is the advantage with this software that you have. So this bit I will just remove it because it is something which I just explained to you to explain how powerful is this tool to handle the big numbers. Okay, right. We'll complete one more problem and close it now. Okay, this is equation solving which we have been learning now with the quadratic form. Then previous problem also like a quadratic only. Now here is the another interesting equation, the 4 equation, 4 unknowns. And do you know what is this equation? Is that typical physics problem where you can have 2 loops are there. You apply the so-called Kirchhoff's laws, get this equation and confirm it that these equations are properly satisfying this Kirchhoff's law, node and loop laws. This is the loop, this is the node, current at the junctions and the voltage at the loops. These are 4 equations. You can I1 and I2 here, and then B equal to I1 Rn plus I2 R2. The 0 voltage is between I2 Rn minus I3 R3, because when the voltage drops from the source, that will be taken plus minus sign properly. And then this B is I1 Rn plus I3 R3 across this total voltage disappear. So this is what the 4 equations. This can be solved for I1, I2, I3. 4 equations, 4 unknowns. As I said, define the equations like equation I1 double equal to equation equal, this is double equal. Okay. Similarly, equation 2, equation 3, equation 4. You can see there is a blue color, these three, and equation 1 is black, which means already that is being defined. That is what it means. And I don't want to use that, that will be clashing with this equation. So therefore, we use the statement remove global all the variables that can be removed. So now you redefine it. 4 equation has been taken now. Now solve. Now you can see in the list I'm putting all the 4 equations. The 3 unknowns are there, but 4 equations are there. That excess equation doesn't matter. It will be simply ignored. If necessary, it will use. Otherwise, it will be ignoring. Find out this I1, I2, I3. That's all. It has been solved. You can cross check, substitute. That you can do it now afterwards, whether this is satisfying all the 3 equations simultaneously or not. 3 equation, 3 unknown answer can be taken and solved. They are one and the same. Okay, you can see here. So which means I have n number of equations, n number of unknowns that can also be solved correspondingly by using this solve statement with defining the proper equation and corresponding variables which you are interested to find. So I1 is connecting this R1, R2, R3 and B, I2, I3. Similarly here the 3 equations. This is the simplest thing that can be done, and it's so quickly one can done. And you can see the theoretical engineering problems can be done very, very comfortably without any fuss. And we can cross check it, substitute back and satisfy or not. That is the cross checking should be possible. Solution can be taken back and then substitute, and it should satisfy. Otherwise, there is something wrong somewhere. Next is another interesting problem which we come across in physics now. You have 3 point charges are arranged in a straight line. Charges Q1 equal to 1 coulomb, Q2 equal to minus 2 coulomb, Q3 equal to 4 coulomb are located at x1 equal to minus 2 meter, x2 equal to 0, x3 equal to 1 meter respectively. Find the point or points along the line where the electric field is 0. So define the values now. X1, X2, X3, Q1, Q2, Q3. E field for the charge 1, E field for the charge 2, E field for the charge 3. Sum. These are all the electric field along a straight line. Add all the 3 electric fields. You can see here. Now the values can be substituted to this E field. Substituted. Okay, I have a E field values available for all the 3. And take that and make a plot. If I find that this is a point where you can see this goes to infinity here, goes to infinity here, where it goes to infinity. Press it. Whenever it's x equal to 1, going to be a problem. Similarly with these things. So now you can see that those points where it goes to large magnitude because it's approaching the denominator, approaching a value which is much, much smaller and smaller. Therefore, it goes up. Okay. Suppose if I make a plot range, okay, all you do see that. So you don't even see that. No, it's not been plotted first. But it should be executed now. Start from here, 99. That is 1, field 1, field 2, field 3, total field, 3 fields together, make a plot. You see what is happening now? What does it mean? Become infinity at those points. Okay. Therefore, you would see that nothing is like it is like a lines which are there. This is what we call the singularity points. So remove this or given range for a plot by y-axis, but without that even it automatically indicates that there's something happening at these points. So this is done. And you can see where it goes to 0. What does it mean? Which means this is your field and this goes to 0 at this point. This goes to 0 at this point. Okay. And of course, beyond that also it goes and touches the axis. Now within this region of say x varying from somewhere between -3 to 2, I find there are two places goes to 0. Solve if field values what is plotted here, take it equal to 0 when find out the real root. I find two different places. One is at numerical value evaluate x values, x solution has been found. This is equal to minus 1.04856, and this is the point at which goes to 0. Other one is 0.444. This is sitting here. It goes to 0. So comfortable. Okay. So now we can select some textbook problems where you wanted to have a field lines of this type of problems. And write down these fields, total fields, and then solve for it. Locate the place where the electric field goes to 0. Like this is possible to solve. And similar problems which you can select, practice them, make sure that you are having a clear picture about this. Several mathematical codes that you have learned, plus parallelly you learn about the physics also. Okay. Now, what is that you are trying to do? Graphical, numerical, analytical. All the three for every problem, whether it is simple or a complicated problem, that should be done. All the three. For example, this problem doesn't say that you plot the x1 and x2, but we have made a graphical plot. It's a clear-cut picture about what is happening. Correct now? You have a clear-cut picture about what is happening through the pictures. And not only that, you try to explore more. For example, what will happen when the acceleration becomes positive, that also been done. And if it is greater than this, what happens? These are additional things that can happen with the help of such shortcuts. Okay? So you can have a couple of questions, some discussions, then we'll close the session. And the Shaheen is around. See somewhere. Shaheen is around. Or... Okay, you can ask some questions now, clarifications from anybody. No questions. Everything is clear for people. Fine. So coordinate is not around. Well, what is the plan now? We go down. Yeah. A previous exercise which you have done. Yeah. Exercise 1. Free fall dynamics we have yet to complete. Okay, we will do it in the next class because we just showed the. I just close this one. Save. Close it. So this is something we have to continue now, or something we have left out. Oh, you're asking double answer. Okay. No. Evaluate this. Yes. Okay. These are all things which we have learned probably. Also, we have seen. Yeah. Here is the point that you would like to check now. You have to understand about what happened to the kinetic energy and potential energy during this dynamics. Please think about it. We try to understand more about these things. The next class. See, for example, mass equal to 1 And you can see what is the kinetic energy versus potential energy. This is the plot. Okay, when mass equal to 1. If it is different masses, 5, 10, 15, 20, 25. Okay, what would happen to this kinetic energy of mv square? This is of mv square. This is mgh, the potential energy. In the parametric form we have plotted. We have a parallel straight lines. Now, here we have to tabulate all these parameters. For example, you need to have a displacement, velocity, acceleration of specific storm, and kinetic energy, potential energy. Then see what is happening to this energy transformation between the potential energy to the kinetic energy, and the mass is increasing. Okay, you can think about it, and you can have some more understanding on the work done by these forces. How do we understand this kinetic energy, potential energy through the work done? Then we will later on, because we are going to use the path that has been taken by this object when it is making a free fall. And how do you link them to in terms of energies and understand what is happening during the energy transformations. Energy being transformed or different masses if you drop it. Okay, what is going to happen, that we would like to understand. Okay, we'll see them in the next class. Okay, fine. So let me have some questions. Otherwise, we can close this session. We'll meet tomorrow. This session notes, I'll send it to Shagin. He will send you people for your reference. Shagin is back. Otherwise, we'll close. You can tell him. Shall I close it now? Hello.
Sir, Shine sir will come now.
Hello, sir.
Yeah, please.
Yeah, sir.
I asked for some couple of questions. Whatever has been done so far. If there is any questions, you can be answered now. Otherwise, I'll send you the details. You can go through them, modify their problem related to that, and then work it out. Get these numbers and cross check. Have some standard good textbooks. And select the problems and try to work out and get a deeper understanding about what is that problem says. What physics that you will get out of that problem that should be learned. And parallelly, you will learn the Mathematica code also. Okay? So,
Yes, sir. Yes, sir.
so we can close down now. So I'll send you the lesson. This lessons, whatever has been done now.
Sir,
Okay.
tomorrow we have the same time?
Tomorrow I'll take Friday, no?
Yeah,
Same
yes,
time.
sir. Yeah.
Saturday, Sunday is difficult.
Okay, sir.
Monday, Tuesday also, because I'll be
Okay,
there
sir.
at my place. It will be little tight for me. Maybe Wednesday only you can start.
Okay, sir.
I'll
Then,
inform you.
yeah. Tomorrow we have class. Then
Tomorrow we can have a class by the
Yeah.
same time.
Yes, sir.
But Saturday, Sunday, Monday, Tuesday will be tight. So I can have it only on Wednesday.
Yes, sir.
Okay? No problem, no?